Problem 64, the last one I'm going to do, is a pretty challenging problem. Not in terms of the amount of work needed to solve for it, but in order to think about how to solve it. But it does incorporate basically everything that we've talked about: conservation of energy, thermal energy with a non-conservative force, and yeah. So let's draw the picture. We get a sort of a ramp-ish that smooths out quickly to a flat-ish surface. There's a block on here, and it's moving this way. Everything is frictionless except for a little piece of a little segment here, which is L, length L, and this point right here is point B. The from the bottom of the friction part to the ground is H. The ground is level with the flat here. This angle, by the way, of the ramp is theta. There's a point here, point A. Well, I'll be. Huh. That's gross. Point A. And we're going to want this height here, sort of the vertical height of the friction part, we're actually going to call B as well. So this is point B, and the height here we'll call B, just for the fun of it. And we'll call the height up to where the block could potentially stop if it makes it past point B. We'll call this height Y. So the problem's weird. It asks if the block can reach point point B. So it's sliding right up here, right? Frictionless, frictionless, and then it hits friction here. It's going to slow down because of gravity pulling down the ramp. But now it's also going to slow down because of friction pulling down the ramp. So if it can reach point B, what is the speed there? Meaning, if it reaches it, does it stop right when it hits B, or can it keep going because it has a positive non-zero speed? Or if it can't reach B, if it stops somewhere up here, or even maybe even before the friction, then what is the height above A? Is it less than H? Is it greater than H but less than, I guess, B plus H, according to what I have here? So yeah, let's do it. L is 0.75 meters. H is 2 meters. Theta is 30 degrees. Mu K is 0.4. And the velocity at A of the block is 8 meters per second. So, mechanical energy at A, how did I get that so straight? Equals mechanical energy at, we'll say, Y. We'll call this point up here Y. So, what type of energies do we got at A? Well, we got some kinetic energy for sure. KE at A. And that's it. We'll say that this is the ground, this is the lowest point, so it has no gravitational potential energy. So that's it. And then once it reaches Y, that's where it's supposedly supposed to stop, if it can get past B anyway. So we'll just put it for now. Kinetic energy at Y plus gravitational potential energy at Y plus the thermal energy that was taken out of the block as it went across L. So this is 0 because it's coming to a stop. So we got 1/2 mv at A squared equals, that's 0, so that's bye-bye, mg, and this height is going to be h plus y. From the ground, it's h plus y to where it stops, plus the thermal energy, which is force of friction times L. Alright, let's well, and that's going to equal, just to get out of the way, mu times, remember ramps? It's not just gravity anymore. The normal force, mu Fn L, the normal force, which is mu mg, but it's not just mg because mg is not going straight down, it's going down the ramp. Sorry, the normal force is perpendicular to the ramp, and that's the cosine component of gravity, so it's not just mg, it's mg cosine theta. Oh. Look at that, masses cancel. So we get 1/2 VA squared equals G. Oh, we know the velocity of A, so I'm going to just start plugging numbers in. 8 squared right here. That equals 9.8. H is 2 meters. We're looking for Y just to see if it's high enough. And plus mu is 0.4. G is 9.8. Cosine 30. L is 0.75. So solve all this for y. Y is the only unknown left. Y is going to equal 1.006 meters. So what's H max? That's like the height. What's the height? So the H max before it stops is H plus Y, which is 2 plus 1.006, 3.006 meters. Does it make it to B? Well, what's the height at B? That's H plus B, which is 2 plus, now B, we can make a little triangle here. Let's do it down here. This is L, this is B, this is 30. That's plenty. We know L. So that's just going to be L, and B is the opposite 30, so sine 30. So that's 2 plus 0.75 sine 30, and that equals 2.375 meters, which, by the way, is less than max height. So it definitely goes beyond B, up farther. So now that we've proven that, the rest of the problem, it asks if it can reach point B, what's the speed there? And we know that it doesn't stop exactly at B, or else these two heights would be equal. So it has some speed. Alright, so we're going to basically just do this again. And now we're going to use B here, basically the height of B, to figure out what the speed is there. So I'm just going to start rewriting it from from here. I'm going to plug in. So we got 1/2 times 8, because it still has the same speed at A. Nothing's changed about that. And that's the only energy there, so nothing's changed about this being by itself. That's going to equal 9.8. Now we're going up H plus B, which we've called HB. So let's just do that. And then we're going to add the work lost by thermal friction. Which is this again. Did I say thermal friction? The work lost to thermal energy by friction. 9.8 cosine 30, 0.75. And we solve for, oh, we know HB. I guess I probably should have plugged that in. That's that right here. Anyway, oh, and we actually can't say, so we got to change this a little bit. We said that this was 0 because we want it to go up to the maximum height. But now we got to add kinetic energy at B back. So this is plus the kinetic energy at B, which is 1/2 m velocity at B squared. M, by the way, is oh, it cancels out, just like it's basically another m term, so we would have had another 1/2 plus 1/2 m v at y squared up here, because this is kinetic energy up here. This mass would have canceled with all these other masses here, here, and here. Anyway, so this mass goes bye-bye. Now we can solve for VB. Just these are all numbers, and we get 3.52 meters per second. And that was an involved problem, pretty difficult, more so in figuring out all the little doohickeys here and in here, but out mathematically not too difficult. Alright, so that's almost 13 minutes, so I'll stop now. Bye bye.